Welcome to SINUMERIK Live, Application Technology Made Easy. Our video series presents SINUMERIK topics in a practice-oriented way and will take up just a few minutes of your time. Today's topic is the deployment of SINUMERIK in various production processes. Job shop production, mold and die making, in other words free-form surfaces, and automation, that is, mass production. You can see this on today's agenda. We'll start with a brief introduction to the general aspects of CNC milling, then talk about CNC programming, 2.5D contours, generating planar surfaces for job shop-based programming. This is followed by free-form generation, mold and die applications, and then finally automation, mass production. As an introduction to CNC milling, here are the basics again. A tool performs the cutting movements, of course, and almost all geometries can be manufactured by milling. To make it easier to distinguish between the individual process technologies, the slides are marked with colors. Job shop production, or single part and prototype production, is yellow. Mold and die making is red, and series production or mass production is blue. All slides without a color marking deal with general topics. A milling operation with CNC machines is used both for single part production and for mass production. The technology, and this is important, is identical, but the requirements for the production process differ. In job shop production, the focus is on planar programming, planar machining for 2.5D contours. These are contours and shapes of manageable complexity that you can calculate yourself. In series production, on the other hand, we also have planar operations, but with considerably more sequences. The result is completely different components that are highly technical, and their production features a very high degree of automation down to the last millisecond, and this of course requires maximum efficiency. Mold and die making is positioned somewhere between the two technologies. It can be used in single part production because parts in mold and die making have the characteristics of a single part. For example, these impellers, which of course first have to be designed and tested at the prototype stage before they can then be widely deployed in any number of applications in industry. A very good example of this is the shape of a car wing mirror. This can be a shape that's used later in plastics injection molding or similar. It's also a typical example of mold making, which can then also be used in mass production. And another very good example of mold and die making and job shop-based programming, the runners of a world champion bobsled. These are unique single parts, prototypes, or workpieces produced in minimum batch sizes. On one hand, we have normal 2.5D contours here. But here too, these rounded edges and the transition to the running surface are typical mold and die making contours, which can be seen very well here. The complexity of milling is subject to technological changes as batch sizes get smaller. Generally, you can say the level of automation increases as the complexity of milling decreases. Of course, exceptions confirm the rule, but overall, this rule can be applied at a general level. With SINUMERIK, we distinguish between two basic ways of programming the machine. There is machine-level programming with shop mill and program guide. This refers to the graphical user interface of SINUMERIK Operate, in which you are guided by a sort of wizard and fill out the cycles in response to prompting to provide the control with the necessary information. This is what we call machine-level programming. And then there's external programming. This is implemented with a CAD/CAM system using the applications during production planning. This means the programs are written externally and then transferred to the machine for execution via a communication link, wireless, LAN, USB flash drive, or any other medium. The functional scope of the SINUMERIK control provides the best possible solution for all production tasks. This starts with the basic milling functions. It also covers contour applications, including the contour calculator. Then, of course, free-form surfaces and any necessary transformations of the moving special axes. And also the mill-turning applications, which are also a unique selling point. Finally, mass production with robot applications, which ensures maximum efficiency. The CNC functions specific to milling are split up into 3 blocks. First of all, the setup functions. These are the so-called setup times that you always require to get the machine ready for production in the first place. And if there are already effective tools to keep the setup times as low as possible, ancillary costs will also fall. Then there's the tool management function. This is used to optimize management of the required drills and milling cutters and other tools used. Here too, the aim is to keep the ancillary and setup costs as low as possible. And then the drilling and milling cycles that are in the functional scope addressed for each area here. 2.5D contours are used especially in tool making and job shop production, but less in mold making. These are planar operations, geometric shapes that are entered directly at the control. They include the geometry and contour calculator, which you can use to describe geometries easily, quickly, and reliably without having to use a pocket calculator. The drawing data are transferred to the control manually and provided with contours, pockets, and other machining technologies. These include the contour cycle, stock removal from pockets with any island contours, and of course, also highly efficient calculation of residual material detection. For this, you take a large milling cutter, rough out the contour, and wherever the large milling cutter cannot enter without violating the contour because of its large radius, the system automatically detects that residual material has been left over. A smaller milling cutter then clears that away automatically. This achieves the greatest efficiency and process reliability in planar machining. All this is done in job shop production and tool making. In automation or series production, these cycles are generated by CAD/CAM programs, imported into the machine from an external source, and the entire calculation of the tool paths is performed externally. You can also bypass the contour calculator by using the DXF reader. This fully automated read-in of digitized drawings in DXF format replaces manual data input. The control automatically generates the geometrical sequences based on the digital drawing. The free-form surface machining in mold and die making are typical machining operations for very small unit quantities or batch sizes, sometimes even a single item. It can of course also be more, but such typical free-form surfaces are not manufactured in mass production. Free-form surfaces are, as previously mentioned, samples for certain molds and dies. In other words, molds and dies with which the products are reproduced in plastic injection molding processes. There are various ways of producing free-form surfaces. The focus of this technology is on achieving a very precise surface. They are mostly negatives of the component to be produced. To achieve this, you can produce very good free-form surfaces with 3-axis machining. Three plus 2 kinematics provide better results and greater flexibility. And also dynamic 5-axis machining, where undercuts can be achieved with any shape and position. If we look at the production process from the blank to the component, what we see is the CAD/CAM process chain. This process is suitable both for single part production, that is, prototype production, job shop programming, and also for mass production. Because a single part can be produced just as well via a CAD/CAM process chain as a component for mass production. And mold and die making, especially in mold making, just doesn't work without the CAD/CAM process chain because many molds and geometries are too complicated to enter into the control system manually. It's mathematically impossible and not feasible in terms of the sheer volume of data. CAD/CAM. CAD stands for Computer-Aided Design and CAM stands for Computer-Aided Manufacturing. The so-called post-processor is connected to this. The post-processor converts the data and transfers it to the CNC control system with the connected machine tool. This means CAD/CAM is virtual. It's the programming of the component. The control and the machine then process this data. The post-processor translates the colorful images shown in the simulation into a data format that the machine or the Siemens control can read. Where does the post-processor come from? It either comes from the CAD/CAM manufacturers who provide the software or from independent post-processor manufacturers or service providers who tailor it to the customer's requirements. This is done both to meet the customer's needs and to match control of the machine. In automation or mass production, the flow of workpieces is fully automated. For example, with multiple clampings, you no longer have to put parts in the machine, machine them, and then take them out one by one. In this case, multiple workpieces are placed on reversible clamping devices and clamped once so that several parts can be machined in one go. This shortens the setup times because clamping times are eliminated. Workpiece conveying systems ensure automatic feed-in and feed-out of blanks and finished parts, or also of semi-finished parts if they're only partly machined. These are moved into the machine area with palletizing systems and positioned precisely on central clamping devices, which are closed either hydraulically or pneumatically, or both. And of course, the connection to a robot ensures maximum efficiency. A robot equips a machine fully automatically without any human intervention, because then no manual operation at all is required. Robot technology is still a special application, but it's being used more and more in every area of industry. Automatic functions and flexible workpiece flows can be further optimized with a transfer line or flexible production line. A transfer line includes cutting and non-cutting processes all linked together. The non-cutting processes could be reforming or bending in this case, which are linked up to the cutting process. Here we're talking about extremely high productivity, but with limited flexibility. On the other hand, we have the flexible production line. This links together single spindle or multi-spindle flexible machining cells. And all these flexible production lines are characterized by high productivity and very high flexibility. As we've seen, milling on CNC machines is performed in job shop production, mould and die making, and in series production. The technology is identical, but the process requirements are different. And that's it for today. Thank you for watching, and see you next time.
Siemens. Ingenuity for life.